Okay, so now we're going to look at the derivatives of two trigonometric functions. And we're going to figure out what these rules are. We're going to end up memorizing the rules, but we're going to prove them or derive them using the definition of derivatives. So we're going to go back to the old limit definition. So we're going to say the limit as h approaches 0 of f of x plus h. So I need to take the x out of my function and replace it with x plus h minus f of x all over h. Now the problem here is going to become that to do the algebra, to simplify, because if we try direct substitution, remember we're going to get sine x minus sine x is 0, and so I get 0 over 0. So to do the algebra to find an h out of the top, or to somehow solve this limit, we're going to need some trig identities. So if you recall, in this case, we need the sine of the addition of two angles. So remember, the x plus h is the angle. So if we think back to this identity, the sine of a plus b is equal to the sine of a times the cosine of b plus the cosine of a times the sine of b. So we're going to use that identity here. So if we rewrite sine of x plus h using that identity, we're going to get sine of x times cosine of h plus cosine of x times sine of h. And then we have our minus sine of x all over h. Now what we're going to do is sort of reorganize our terms up top. So we've got sine of x cosine of h minus sine of x plus cosine of x sine of h all over h. So now we're going to apply some properties of limits. We're going to say, we're going to decompose our addition. We're going to look at this as addition of fractions. So we're going to have sine of x times the cosine of h minus the sine of x all over h plus the cosine of x times the sine of h. Oh, whoops, I got to write the limit in front of that. The limit as h approaches 0. So yeah, that's good, all over h. So now if I further apply these first I want to factor, limit as h approaches 0. You're going to want to factor out a sine of x. You don't necessarily need to remember how to do this. You should just be following along. So we're writing a proof here. So I noticed that there's two terms here, and they have a sine of x in common. So I'm going to common factor out a sine of x. What I'm left with is, in this first term, if I divide out a sine of x, I'm left with cosine of h. Minus, in this second term, if I divide out a sine of x, I'm left with 1 all over h. Over here, I still have the limit as h approaches 0 of cosine of x times sine of h over h. Further applying our properties of limits, I could say the limit of sine of x times the limit as h approaches 0 of cosine of h minus 1 over h. So because this is multiplication, I could think of this as sine over 1 times that fraction, right? This is one of our famous trig limits. That's why we did that. If I apply this over here, I could think of this as cosine of x over 1 and decompose that multiplication of fractions. So I get limit as h approaches 0 of cosine of x times the limit as h approaches 0 of sine of h over h. And on our tests, we were really bad at applying the properties of limits. We did very badly on trying to figure out, like, rewrite this, applying your properties of limits. It's just a property, it's a property, it's a property. I haven't done any limits yet, so we have to figure that out. So you can ask me about this if you're not sure. Now I can do all of these limits independently and then take their answers and do the arithmetic, the multiplication, the addition. So the limit as h approaches 0 of sine of x is sine of x. If I do direct substitution, there is no h to plug 0 into, so I just get sine of x. This is a famous trig limit. It's 0 plus, again, over here, if I plug 0 in for h, there is no h, so it's just cosine of x. And this is a famous limit, which is 1. So the derivative ends up being cosine of x. So f prime of x equals cosine of x. That's a rule that we're going to just sort of remember, that if our function is sine of x, our derivative is cosine of x. So remember, this is a verb. It means what's the derivative of sine of x? It's equal to cosine of x. Now let's a similar argument will produce our derivative for cosine of x. So I'm going to buzz through this as well. So I'm doing f of x plus h minus f of x all over h. We're going to apply this trig identity. If you have the cosine of a plus b, that's going to be equal to the cosine of a times the cosine of b. That's an identity minus, it's not plus, sorry, minus sine of a times sine of b. So since we have the cosine of a sum of angles here, we're going to apply that thing. So it's going to be the limit as cosine of x, cosine of h, minus sine of x times the sine of h minus cosine of x. Now it's a similar thing. I'm not going to go through every single step. I'm going to separate. I'm going to take this cosine of x times cosine of h minus cosine of x, and I'm going to put it to the front, and I'm going to factor out the cosine. So I've got cosine of x times. When I take a cosine of x out of this, I just have cosine of h. When I take a cosine of x out of that, I get a minus 1. Minus sine of x times sine of h, the whole thing over h. So again, if I apply the properties of limits here, I'm going to get the limit of the cosine of x times cosine of h minus 1 all over h minus, so I'm decomposing this subtraction here, the limit as h approaches 0 of sine of x times sine of h. So I apply the properties one more time. Again, whoops, that says h approaches 0. Again, think of this as cosine of x over 1. So times the limit as I decompose the multiplication of fractions, cosine of h minus 1 over h, and that's a famous limit, minus the limit as h approaches 0 of sine of x. I'll think of this as over 1. So if I decompose the multiplication, it's going to be times the limit as h approaches 0 of sine of h over h. That's also, so these two are famous limits. That one's 0 and that one's 1. So we know that if we do direct substitution here, there's no h to plug it into. So I get cosine of x times this limit is 0 minus, if I do direct substitution here, I get sine of x, and then this limit is 1. So my derivative ends up being negative sine of x. So that's going to be something that we're going to memorize. So this was a proof. You need to know that the derivative of cosine, so that's a verb, take the derivative of that function. So the derivative of cosine is negative sine of x. All right, so we're going to use that along with our power rule. Remember, power rule says to take the derivative of, I'm going to put a coefficient in front, ax to the n. We can apply properties of limits because derivatives are like limits. They're defined in limits. I can pull that coefficient out, just like we do with limits. That's a property of derivatives. And then just take the derivative of that guy. So then I get a times the derivative of that by power rule is here. And then I can multiply the a times the n. So it becomes a times n x to the n minus 1. Another way to think about power rule. So that if I want to take, I can kind of connect. Let me get rid of this arrow. I can connect taking the derivative of that term all the way to there. The n comes down and multiplies by the a. I recopy the x, I reduce the power by 1. Let's apply some of these. So now they want to know a specific derivative, a specific tangent line. So it says find the equation of the tangent line. Okay. So we're going to have to put this, to find the derivative of this function, keep in mind we have to put it into polynomial form by multiplying it out. But before we do that, we want to find the point of tangency. We talked about this when I reviewed with each one of you in class the other day. Remember, to find the point of tangency, I can plug the x value in to f. So I get 2 times negative 1 minus 1 times negative 1 plus 1 squared. So I end up getting 0, it looks like. So that means I know my point has an x value of negative 1 and a y value of 0. Remember, that's f of negative 1. That's how we got that. So there's our point of tangency. Now we need the slope of the tangent line. We can apply power rule for a shortcut here, but first we got to put it into polynomial form. And once we have our derivative, then we can find the slope of the tangent line. So I've got to multiply this thing out. So I'm going to say it's 2x minus 1 times x plus 1 times itself. So that's what I get when I square x plus 1. Now I'm going to multiply the 2x minus 1 times that result, combine like terms, and I should get 2x cubed plus 3x squared minus 1. So I have to do all that prep work just to apply the shortcut of power rule. So now I can do the derivative. Notice the change in notation from here to here. Power rule, 3 comes down, multiplies by the 2. Recopy the x, reduce the power by 1. 2 comes down, multiplies by the 3. Recopy the x, reduce the power by 1. The derivative of a constant is 0. I don't need to show that. So there's my derivative. So now to find my specific tangent line, I can plug negative 1 into it. So I get what? 6 minus 6. Am I also getting 0? So the slope of my tangent line is 0. So now I know that the equation of my tangent line is y equals, if I use the point, y equals 0. Why do I know it's that? This tells me with a slope of 0 that it's a horizontal line. And then if it's a horizontal line, it's going to be y equals whatever the y coordinate is. All right, let's try the next one. So I got to first find my point of tangency. So that means I do f of pi over 2, and I get 4 times, I won't put the parentheses there, sorry, 4 times the sine of pi over 2 minus pi over 2. So that's going to be equal to 4 times sine of pi over 2 is 1 minus pi over 2. I'm getting 4 minus pi over 2. That is our y value. So I'll write my point of tangency as pi over 2 and then 4 minus pi over 2. There's the point. Slope of the tangent line. Well, first I need the derivative. So I'm going to say f prime of theta. So I'm going to recopy actually f of theta just so I can kind of refer to it here when I find my derivative. 4 sine of theta minus theta. So when I do the derivative of 4 sine of theta, remember that the derivative of sine is cosine. Oh, whoops. So using that, even if I have a constant in here, right, the derivative of 4 times sine of theta, what I want to do first is pull the 4 out of the differentiation. And I can do that because derivatives are rooted in limits. And I can pull a constant through a limit, calculate the limit, then multiply the constant. So now I know that the derivative is going to be 4 times whatever the derivative of sine is, which is cosine. So what I say in the end is you don't have to write all this out. In the end, if you're doing a constant times sine, the 4, the constant, just comes along for the ride, and you take the derivative of sine. Or more generally, for any function, if you have 4 times f of x, and you want to do the derivative, the 4, the constant, will just come along for a ride, You can do 4 times whatever the derivative of that function is. In this case, our function sine of theta. So let's look at that. 4 comes along for the ride. The derivative of sine of theta is cosine of theta minus, now theta is just like your x. So if my derivative was negative x, if my function was negative x, my derivative would be negative 1 because it's just a line with a slope of negative 1. So that's my derivative. Now to find the slope of the tangent line, I've got to plug pi over 2 in there. So cosine of pi over 2 is 0. So the slope of my tangent line, doing that, is negative 1. So now I want to write the equation of my tangent line. Equation of my tangent line is going to be y minus the y value, which was 4 minus pi over 2. I got to put it in parentheses so that negative sign works out correctly. Equals the slope, negative 1 times x minus my x value, which was pi over 2. That's the equation of the tangent line. All right, let's go. Keep going on here. So we got point of tangency. I'm going to do g of pi equals 2 pi plus 3 cosine of pi. So g of pi equals 2 pi plus 3. Cosine of pi is negative 1. So I get 2 pi minus 3. So my point of tangency is going to be pi, and then 2 pi minus 3. Now I need to do my slope of the tangent line. Remember, to write the equation, I need my point, and then I need my slope. So the slope of the tangent line will be the derivative. So if g of theta is 2 theta plus 3 cosine of theta, g prime of theta, theta is your x, so the derivative of 2x would just be 2, so that's that. The 3 comes along for the ride. I'm not going to put the plus there because now I do the derivative of cosine is negative sine, so I'll just make that a negative out front there. My theta, when I do a trig function, it should be, my angle should be in parentheses. So there's my derivative. Now I want to plug in the x value pi. So sine of pi is 0, so I end up getting 2 for my slope. So when I write my equation of the tangent line, I get y minus 2 pi minus 3. Again, because of the minus sign, I really need my parentheses there. Times the slope times x minus my x value, which was pi. All right. I'm going to go ahead and do the derivative first on this guy before we do the point of tangency and the slope of the tangent line. So I got to convert h of x into a polynomial type function. So the first thing is I want to change my root power into a fractional power. So remember, that's like a 2 if there's nothing there. Then, let me see here. I can charge that thing. Okay, so then I want to simplify this so I can think of that as 2 halves. So I can subtract the powers. I'd get 2 over x to the 1 half. And then I can't have my x in my denominator, so I'll bring it up. So that's the h of x that I want to use to find my derivative. Okay? All right, so now for my point of tangency, I'm going to plug my x value 2 into my original function, and I'll use that form. Oops, I wanted to plug 2 in. So I will get 4 over the square root of 8. The square root of 8 simplifies to what? 2 times the square root of 2. So I end up getting 2 over root 2. And then if we want to simplify it, or I should say rationalize it, you would get 2 root 2 over 2, which would just be, what, root 2, I think? Is that right? Yeah. So then, that's my point of tangency. The x value was 2, and the y value was root 2. Now, I already did the derivative, so the slope of the tangent line should be pretty easy. H prime of x was, did I not do it? Oh, I didn't do it. I just simplified to the form that we're going to use right here to take the derivative. So I'm going to apply power rule to that. The negative 1/2 is going to come down and multiply by the 2. That'll give me a negative 1 x, and then I reduce the power by 1, so I'm subtracting 2 halves, so it's x to the negative 3 halves. I'm going to change it to negative 1 over x to the 3 halves. Then I'm going to change it to the square root of x cubed on the bottom. Okay, so now I can plug my x value of 2 into that guy, into the derivative. So I get negative 1 over 2 cubed, square root of 2 cubed. I get negative 1 over the square root of 8. We know that square root of 8 is going to be 2 root 2. If I rationalize, I get negative root 2 times over 4. So I don't know if that's any more simple, but we could use that. That's the slope of the tangent line. Let me highlight that guy. So then the equation of the tangent line is y minus, the y value was root 2, equals the slope times x minus 2, which was the x value. Let me see if I can pause this so I can go charge the pencil. I think I can. Alright, I'm all charged up. Let's see, let's do 2 more problems where we're going to kind of review a little bit of other stuff as well from this unit. So given the equation of a function, how might you determine the values at which the function has a horizontal tangent line? So what we would do is horizontal tangent line means that there's a relative maximum or minimum at that spot on the graph, and that would mean that the derivative of that function would have to be equal to 0. So that's how we can find if there's a horizontal tangent line. We're looking where our derivative equals 0. And even if that's the case, it may not always mean that there's a maximum or a minimum, but it can still have the horizontal tangent line. I'm just kind of saying that that's kind of the typical garden variety time that it happens. If there's a relative minimum or a maximum, that's going to happen a lot of the time. We're going to look at another way, another spot where it might happen. So first of all, let's just write this out so you know what to do when you want to find a horizontal tangent line. So we'll say if f of x has a horizontal tangent line, that means its slope of that line has to be 0, which means the derivative will be equal to 0. So the steps would be, first find the derivative, then you would set the derivative equal to 0, and then solve for x. That would be the values at which the values for x at which the derivative has, at which the function has a horizontal tangent line. And again, that typically or can occur at a relative max or a min. It's not the only time it occurs. We'll see some other stuff here where it could never occur, or there's a spot where it happens, but it's still not a max or a min. So let's try this on this first one. So what we said was take the derivative first. So if I apply power rule, I get that. Set my derivative equal to 0 and solve for x. So for this guy, I'm going to get x squared by itself. Then I'm going to square root both sides. So I should get two answers, plus or minus the square root of negative 1/3. But you cannot square root a negative number. So there are no solutions. Which means there is no spot there's no value of x, I should say, or there's no x value for which the tangent line is horizontal. Why is that? Well, if you know the graph of this guy, you know that it's always increasing. And a little bit of review of what we've talked about is if a function's increasing, then its derivative is positive. So if this function's always increasing, that means its derivative is always positive. If the derivative is always positive for all values of x, it could never be 0 because 0 is not a positive number. I took the liberty of showing you the graph of this function with where I can look at the tangent line. So as we look at any x value anywhere on this curve, you can see the function itself, the orange curve, is always going up, which means the derivative is always positive. The slope of the tangent line is always going to be a positive slope because the function's increasing, right? Always positive slope. So this function never gets to a horizontal tangent line, never has a slope of 0 because it's always going up. All right, so there's a look at what just happened. Now let's do our last one here. At what values of theta will this function have a horizontal tangent line? So again, we're going to find the derivative, set it equal to 0, and solve for theta. So the derivative is going to be 1 plus the derivative sine is cosine of theta. We're going to make that equal to 0. And these are cyclical functions, so typically they'll give us some type of interval to find our x values in, because with trig functions, once we find a 0, it can just keep repeating forever, right? So now to solve this, I want to say that negative 1 equals cosine of theta. Where's the cosine value equal to negative 1? That's really what this is asking. I mean, we could do the, if you can use your calculator, we can do, you know, the inverse cosine on both sides. And so over here, this will just give us a number. And over here, we know that the inverse cosine undoes the cosine, and we'll have theta equals. So what this is doing is saying, what angle has a cosine value of negative 1? And you don't have to write all that out. You can just kind of get there from there if you're not using a calculator. So the cosine, the angle that has a cosine value of negative 1 would be pi. And then it would happen again if we added another 2 pi to that. So at 3 pi, but 3 pi is outside that interval. So our answer is theta equals pi. So that is a spot on the graph where we have a horizontal tangent line. Now remember I said usually horizontal tangent lines occur where there's a relative max or a minimum, but in this case that is not the case. What happens here is sometimes we could have something called a point of inflection, and that's where concavity changes. We'll get into that a little later. It's not a max or a min. It's where the graph changes from being like curved upward to being curved downward or vice versa. You could get a horizontal tangent line there at a point of inflection. Let's take a look. This thing, if I change my function for x, did it die? This is dead. Nice. Decimals sucks. Let's try again. Yeah, I was watching Sunday Ticket. Watching the Eagles lose. Unbelievable. I have that graph saved in here. I'm signed in. I saved it as tangent line notes that day. So I'm going to put in our new function here was theta plus sine theta. So x plus sine of x. And this is a look at this graph. So you can see that the graph is always increasing, but at these little spots here, it does, the tangent line gets horizontal. It does have a derivative of 0. That's called a point of inflection because, like I said, it changes the curvature. Like on this part, I would call that concave down or opening down, and then after the point of inflection it's concave up. We'll talk about what that means a little later, but this is the point where you have a horizontal tangent line right at pi. So 3.14, can I get there? Stop. Oh, I had it. 3.14. I want to label that point. There we go. I'm just annoyed. I want to get that. I can't do it. Yes. No. Oh, I had it. There it is. It gets to be a horizontal tangent line right there and every other spot, but this is the only one on our interval. So you can see that it's not a maximum or minimum. I just like to point that out. So that's the end of those notes. Thanks for listening to my nonsense.